The purpose of this lecture is going to be to talk about electrical resistance. Now, we've talked about conductors, we've talked about insulators, we've said that conductors allow charges to flow. And we like to just think of wires as being, hey, we've got electrons we want over here to flow, we want them to go over here, just hook them up with a wire, forget about it. The problem is, we have to remember that these are made up of atoms and molecules, and how electrons interact with those maybe isn't as simple as we think. It turns out that almost all materials, with one exception, a category called superconductors, they don't transmit all of the energy that you put in per charge. Some of that energy is lost in other forms, such as heat. So why is that? Well, I've got a wire here, and let's say I hook my wire up to a battery. Now I've drawn the crystal structure of the copper here. So to remind us that it's made up of atoms. So I think it's pretty clear what's going to happen. Electrons are going to flow out of the negative. They're going to flow into the positive. So there's going to be a pressure for electrons to be going this way through the wire. We'd like to say that that's like a river. They go in just one direction. But it's not really true. What's actually happening is they are going all around. And there's a very small drift speed that means over time, they actually do make it from one side to the other. But all of this moving around, it knocks the copper atoms around, it gives them kinetic energy. And the kinetic energy of atoms is actually what temperature is. So what's happening here is this wire is converting some of the electrical energy that I wanted to go through it. It's converting it to heat. And that means if I have a load, and I really should have a load here, the energy that this light bulb is getting is less because the wire is heated up a little bit.
I've got an interesting antique here called a slide wire rheostat. And it's going to really help us understand the relationship between the energy per charge, or the voltage, and how fast that charge flows through the circuit, the current. And what a slide wire rheostat is a big coil of wire, and it's wrapped around this drum. And then there's this thing here that can slide on it, which is called the wiper. So it can just kind of go up and down. There's three places you can hook electricity up to flow through. You could hook electricity up here and here, in which case it might go through the entire coil of wire. But you could also hook it up between here and here. The connection for that is this right here, because this is hooked up through metal. And the reason you would do that is because it makes a connection with the coil of wire there. The path of electricity through would be here, around the coil, and then up through this and out. And by sliding this, that means I can actually change the length of the wire that stuff has to go through.
You can imagine the various things that would contribute to how long it takes an electron to ping pong its way through here. So the things that contribute to resistance, which we give a capital R, the longer the wire is, we expect that to increase resistance. So I'll put an L there for the length of wire. The fatter the wire is, you'd expect to decrease resistance because it wouldn't have to be all trying to go through a few atoms. There'd be more atoms for it to go through. So we expect that the fatter we make the wire, the more area, would decrease resistance. And then lastly, what type of atom is it? We expect each material is going to behave slightly differently. So there's a factor we call resistivity. It gets the Greek letter rho, and that's just dependent on what material you've got. These three things together contribute how much resistance something has.
So let's see if we can use that to figure out some relationships between voltage, energy per charge, and then current, the speed of charge. So I'm going to build this circuit here. I'm going to put 25 volts across this rheostat. I'm not going to hook up this end at all. I'm leaving it bare. And I'm going to hook the wiper up to the negative of the power supply, and I'm going to hook the positive up to this end of the coil. I want to put some meters in there too. I've got my voltmeter and my ammeter. So let's remember how they have to go. The voltmeter goes across the circuit. And the ammeter actually has to go in the circuit. So that when I put it together, the electricity is going to flow through part of the rheostat, out the wiper, through the ammeter, and back home. So that'll be the current. Alright, let's start putting that together. Hook that up here. And as you can see, we instantly got a current. It looks like it is about 0.2 amps. Now we need to put the voltmeter across. And as we can see, we end up with 25 volts. So let's try sliding the wiper arm and see what happens to voltage. Whole lot of nothing. No change at all. It stays about 25. Let's watch what happens to current. It's like the closer I get it over there, the more the current goes up. And the more I bring it back in this direction, the current drops. So what's going on there? And when I have the slider over here, that means electricity has to pass all around this hundreds and hundreds and hundreds of times before it gets to go back to the power supply. And apparently that's slowing down the current. But if I shorten the length of wire, apparently that speeds the current up. Resistance is the ability of an electronic device to impede the flow of charge. And as we can see, current is inversely proportional to resistance. I've got the same circuit as before, but I've actually added in a way to control how much energy per charge, how much voltage there is. It's actually just another rheostat, although it looks pretty different. But what's important is what relationship in our circuit there is between volts and amps. So let's watch. Right now, I've got the volts at 20, and the amps are reading about 0.7. Watch what happens as I increase the voltage. Do you see the amps going up? So what that tells us is that current is proportional to voltage. Let's see if we can combine those two observations together. So our experimental observations were that current was inversely proportional to resistance and directly proportional to voltage. So if we combine these together, we expect that current should be proportional to voltage over resistance. And it turns out that current is actually equal to voltage over resistance. By knowing how fast charges are flowing versus how much each charge is being pushed, we can always calculate how hard it is to push charges through. Likewise, if we know how hard we're pushing and how hard it is to push, we can calculate current. If we know two of these variables, we can always figure out the third. It's usually written a slightly different way. Voltage is current times resistance. And in this form, it's usually called Ohm's law. So Ohm's law is the relationship between voltage, current, and resistance.
So a lot of times the losses here, which we call resistance, they're kind of nuisance losses, and they're something that we have to try to design devices to not lose these energy losses. But there are sometimes we remove energy through heat on purpose. For example, this is what a toaster is. A toaster uses electrical resistance to get really hot and toast your bread. Some types of electric heating work the same way. Also in electronic devices, we have something called a resistor. And I'll hold up some resistors here. I don't know if you can see them. They are right here. And these are used to take energy out of the system as it flows into various components so we don't put too much energy in.